Two things. Very simple. First one. In your networks, in order to understand Prim's algorithm, you need to be able to identify what we call a tree. Okay, so when is it a tree? Or when can you say that you have a tree? Shh, listening. A tree is when you have no loops, no multiple edges, or cycles, meaning that you don't come back to the same spot. What's multiple edges? An example would be something like point B has that links to multiple edges there. Okay, so we say that a tree is simply a network that doesn't loop, essentially. Okay, now one of the things that you want to identify is what we call a spanning tree. Okay, so a spanning tree specifically means that all vertices are connected. Okay, listening. So a tree is that you can connect edges, but not all the vertices are connected. A spanning tree means that all the vertices have been met. In terms of its application, it's like saying if you had houses on a street or in a suburb, you want to make sure that the postman would deliver every single place once, but you don't want them to skip on any of their houses. They have to go through it. What you don't want is for them to repeat edges. Okay, so you want them to do a nice smooth trail and then finish. Okay, that is an example of a tree, but a spanning tree. There are multiple ways of drawing it. I mean, you can draw it like this, like that, like that, like that, like that, like that. That technically is a spanning tree because it connects all vertices. Now, what you're going to be learning in Prim's algorithm is that given the scenarios, so over here, remember each edge is a weighting. That weighting could mean time, could mean cost, could mean distance. What we want to find, okay, what we want to find in Prim's algorithm is we want a spanning tree with a minimum weight. Okay, so what is a minimum weight? It just means what is the shortest path? What is the best way so that you can connect all of them in the most efficient way you can? Okay, so if you think it in terms of pipelines, you know, if I needed to run pipelines to every single house, I want to make sure that every house has been a connection, but also save on resources. So what I don't want is to use a lot of resources for piping when I can do it for less. Okay, so that's essentially the idea. So the first exercise gets you to identify what is a spanning tree. So there's multiple ways of doing this. And then in the next exercise, which is what you're really needing to learn from this dot point, is how do we get a minimum spanning tree? And there is an algorithm for it, but really you can do it by inspection. Okay, so let's start off. One of the properties that I want you to copy in your notes. For a tree to exist, we also know that the number of vertices will have n minus 1 edges. And that kind of makes sense. If you think about it, if I have two dots, two vertices, well, of course, I only have one edge. So there's always going to be one less than the number of vertices. So ideally, a tree would have the most, in terms of when you're connecting them, it's always going to be one less than the edges. So over here, as an example, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. I expect that I can actually connect all of this with 8 edges only. I don't need, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, that's unnecessary. So that means there are 5 edges that I can remove from this diagram and still connect all of the vertices together, which makes it a spanning tree. That's what this question is asking you to do. So they say draw one spanning tree for the graph shown and then calculate the weight of that spanning tree. So if I know I just need to remove 5, because remember it's 9 vertices minus 1 gives me 8. Right now I've got 13. 13 minus 5 gives me the 8 edges I can. So what can I do? I can do things like, I can take that one off. Okay, so I just took off this one from here to here. So I can still get to that vertice by going 2 and 1 rather than going 6. Okay, so I can go 2 and 1. I can say, maybe I can take off this one. That still works. Because remember, we can't have loops. right? So a tree cannot have any loops, no multiple edges. I'm still going 1, 2, 3, 4, I've connected those ones there. I can now maybe try to connect, maybe I'll take off this one. So this is now, there we go, that's now 3 edges I've taken off. I've got 2 more to take off. Okay, and I can choose to take off maybe this one. That's 1. And at the moment I've got a loop. This makes a loop. So I can't have that. All right, so maybe the last one I take off is the 5. This is an example of what we call a spanning tree. Okay, so I've connected every single vertex, every vertex has been connected, and I should only have 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. So all edges have been connected. But is this the most efficient? Is this the minimum spanning tree? I don't know yet. That's what we're working on this exercise. We're going to try to find the best tree, and there's only one answer for that. There's multiple answers for a spanning tree, but there's only one that is the minimum. Okay, so here, in this particular case that I drew, I just randomly took off a few. So I've got 2 plus 3, so I've got 2, add 3 in terms of my weight. Oh, sorry, I didn't do 3. I did 1, I did 3 and 4, 2, 2, 5, and 2. So let's add them together. 1 plus the 3 plus the 4 plus the 2 plus the 2 plus a 2 plus a 5. Right, so that gives me what? That's 4, 8, 10, 14, 19. So I got 19 as my weight. Okay, so I've got 19 as my weight. That's for my spanning tree. So I've answered part A, part B. But is this the minimum? Okay, is this the minimum? I don't know. And so there must be, I haven't actually tried to find the minimum. I was just taking off different branches. Okay, so what's Prim's algorithm? It looks a bit intense here, but it's very intuitive. This is all they're going to teach you to do. Prim's algorithm, to find the minimum spanning tree, your goal is, you can start anywhere on this graph here, but your goal is to get the minimum distance that you have to connect to every single dot point. So how do you do it? This is what Prim's algorithm is. You pick a point, doesn't matter where. So let's say I'll start off with A. You pick a point, and then from that point, you look at all the connections. You got A to B, A to D, A to F. Which of those 3 has the most or the smallest weight? That's all you're choosing. So I can see out of those 3, 2 is my smallest weight. So I'll do that one. So now I've got A and B. Those are my 2 points. So what's the algorithm? Now that I have A, so I chose A, I looked at the smallest connection I had. Now I have A and I have B, and then you ask yourself the same question. You say, from now, connection at B and A, what is my smallest connection here? So A again, I still have a connection 5, 6. Connecting to B is now 6 and 8. Out of those, all of those options there, which one has the smallest weight? Okay, so the one with the smallest weight currently is a 5. So this is my next one that I'm going to choose. That connects A to D as my next weight. So the algorithm resets again. Now I have A, B, and D as the ones to consider, and I look at all the connections from A to B to D, and I want to choose the smallest value. Okay, so let's look at the connections to D. I'm going to use a different color so you can see. We're going to do D. D is connected to this, to that, and to that. So out of them all, I've got 8, I've got 6, I've got 3, I've got 6, I've got 7, and I've got 6. Which one is my best option out of the ones I've just got now? 3. So that's now my next best choice. So I'm now going to connect C, and that brings me, I'm just going to rub this out so I don't confuse you all there. I'm just going to take this out. And so this is now my connection. But can you see, I'm going, each time I'm doing it, I'm ticking off a vertex, but I'm also choosing the best weight. That's what makes Prim's algorithm, that's what Prim's algorithm is. So each time you pick a new vertex, you have now more options to consider. Okay, so out of them all now, I'm at C. So again, I look at all the numbers. C has a connection of 5. Okay, so I've got 5 as my connection. I've got 8 as my connection. but I don't need 8 because that connects back to B, so really I wouldn't do that. So I've got C, D still connected to E by 6, D connects to F by 7, and I've got A connects to F by 6, and that's so far my options at the moment. Okay, that connects with C. So what's my best option here? I can see that out of all the numbers, 5 is my best option at that point compared to 6, 7, 6. So I would then say C to E is my next best option. Okay, and then from point E now, I'm collecting that. So I'm saying, okay, so apparently E was the best one out of all 5, 6, 7, and 6. Now I ask myself, E, including all the other connections, which now I have 2 included, which one is my best option there? And we can see it's 2. So that is why when I rub it all out right now, so remember how many vertices do I have? I have 1, 2, 3, 4, 5, 6. Then I expect 5 edges. And I've got 1, 2, 3, 4, 5. And these are my best 5 edges, which is called the minimum spanning tree. So it's a tree. It's spanning because you connect all the dots or all the vertices. And it's a minimum because it's the smallest weight that I can get out of it. There's only one answer for that. Okay, so this exercise that you're working through, there should only be one answer in them all. That's what I want you to practice. So it's the idea of the more vertices you have, the more numbers you're going to compare to find the best version that you can get. Most of it you can do by inspection. As you're going, you'll probably choose the best option anyway. But that exercise, that worksheet I just printed out, that's a mixture of Dijkstra's algorithm and also Prim's algorithm. And you know the difference when they ask you to find the minimum spanning tree or they ask you for the shortest path. Okay, shortest path is Dijkstra's, and you would do it by inspection, not the table, unless you want to. And then you also have spanning tree. And that finishes off chapter 14. Okay, and then we only have chapter 15 left. That's where the flow problems and all that gets a bit trickier. So I'm thinking of starting next week. And so therefore this Friday, we'll do the formative on that, and I'll probably let it for you to take home and just to have a look and then hand it back to me on a Monday so that I can mark and see where you're at. But next week, the aim is to smash out chapter 15, 4 exercises, I think, A, B, C, D, no, 5 exercises, A, B, C, D, E. Yeah, 15, chapter 15, all the way E, and that's it. We're done with unit 4, and that's it for the year, pretty much. Then it's all done. And then it's all about prep for the exam. So you only got 5 more exercises after this, and we're going to finish by next week. The SAC is predicted to be week 9, but I know a lot of SACs are coming on that day, so it might change.
Yeah, that's an awful week.
Very. But everyone's trying to finish. I know everyone.